Hey gang, and welcome to the Worksheet Solutions Walkthrough for the worksheet Deducing Structures from Proton NMR Spectra Part 2. Alright gang, assuming you've already tackled Part 1 in all of its glory, welcome to Part 2. So if you're here, you're searching for answers, right? And it is Worksheet Solutions Walkthrough. That is where I go through the worksheet, you know, that the video is about. I'm going to show you how I arrived at all the answers, explaining my thought process along the way, and hopefully giving you a full explanation that you have been searching for. But enough of me talking, let's get going. Okay gang, problem 1. So if we take a gander here, right, we look at our molecular formula and step 1, degrees of unsaturation, right? Follow the process, trust the process. So in plugging in our numbers here, whoa, we see we have a whopping 4 degrees of unsaturation. Now, I hope that, you know, if you've done the past worksheet, the 4 degrees of unsaturation can be a very special case, but let's think about it, you know, after we fill out our chart and see our chemical shifts. So we see that with 14 carbons, we only have 2 signals. So we must have tons of symmetry going on here, right? So with A and B, we fill out our chart. We see we're dealing with something way downfield, just above 7, and something very upfield, right? This is very de-shielded, that's very shielded. Again, I'm just gonna try to pummel the terminology into your heads. So, right, we see around, you know, in the 7 area, I probably drew this more to the closer to 7 than it should have been, or whatever. 7.3, it's a doublet. So we have a four, you know, integration number 4. We have one neighbor because it's a doublet. So when you are in the low 7s, that is aryl hydrogen territory, meaning you are a hydrogen directly off of a benzene ring. Don't get confused with the benzylic position, right? I'm talking about directly attached to a benzene ring. That is a very de-shielding effect because you have this delocalized, you have a pi system of electrons here. You have so much electron density in there that is going to de-shield your hydrogens. Okay, so you have that going on, as well as the massive peak that corresponds to 18 hydrogens. It's smack dab on 1. It's a singlet, no neighbors. Okay, this is key. This screams terminal CH3 with no neighbors. Okay. If this is a CH3, then we must have 6 terminal methyl groups. And if you are coming from part 1 of the NMR drawing worksheets, we saw how we could have that if we had a T-butyl group. So if we had 2 T-butyl groups, this might work out for us. So we know we're going to have a benzene ring. Oh, the other reason why a benzene ring is so excellent for this situation is once I draw it, you'll see why. How many degrees of unsaturation? The ring. First double bond, second double bond, third double bond. A benzene ring is an automatic 4 degrees of unsaturation. So if you have 4 degrees of unsaturation and you have a characteristic peak in the low, mid-low 7s, you're probably dealing with a benzene ring, especially when you have this much symmetry, okay? So I'm actually gonna give myself a little bit more space. I'm gonna draw a smidge up here. Okay, so we also need to make sure when we place these extra carbons, so that takes care of 1, 2, 3, 4, 6 carbons and 6 hydrogens as well, okay? So we need to fill in where we think these T-butyl groups go and also make up the difference with our carbons. We have 8 carbons left, which is great because we were talking about potentially having something like this. So this is a group of 4 carbons, okay? So 1, 2, 3. So these 3 would abide by the characteristics of this peak right here. There's no neighbors at this position. So CH3, 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 that is 9 hydrogens right there. But we need this peak to correspond to 18. So if I made it very symmetrical and did this, not only do we have 3, 6, 9, 12, 15, 18, these all correspond to 1 peak. These are all peak A. What I just did was also make sure that now, so these are all equivalent positions. Here, I'll dot them. And I will asterisk now what are all equivalent positions right here. So I just made this position equivalent as well. So B is taken care of. But did I also just take care of A? And the answer is yes. You can see the integration number is 4. We have 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. And they're all aryl. So this problem is done. So it's big on symmetry, but I liked it. I wanted to throw it in to reinforce the fact that if you have that singlet at 1, you have a T-butyl group, right? You have a bunch of CH3s, however many, depends on the integration number, but you have a bunch of CH3s that don't have neighbors. And I liked it because it showed us, you know, a case where you have 4 degrees of unsaturation, you had that characteristic peak in the low 7s, so introduce some type of benzene proton NMR problem. But I bet that was no challenge for you. However, we are on to problem 2. Okay, gang, problem 2. So if we take a look here, right, first and foremost, let's get our degrees of unsaturation in order. So given this chemical formula, C7H12O, we got, you know, we can calculate 2 degrees of unsaturation, right? So remember, rings, double bonds. So if we take a look here, right, and then we digest our spectrum and regurgitate out, or, you know, spit out our table of wisdom, we have some interesting things. So very notably, right, if we just go row by row real quick, we're going to encounter a chemical shift we haven't really seen before. So when you have something in this 5 range, and you can see we have 1 hydrogen that corresponds with that signal, that is going to be, you know, at least in this case, a vinyl hydrogen, right? Vinyl meaning it's going to be just off of an sp2 carbon, okay? So you get that right from your handy-dandy chemical shift table. So then, going through, we see B and C are kind of in the, you know, high 1s, low 2s, and we see specifically that B has an integration number of 3, it's a singlet, and it has that alpha to the carbonyl type chemical shift, so that's why I believe it looks like it's alpha to the carbonyl, and on one end it's terminal, right, because the chemical shift is 3, so it can't be in the middle of the chain if it has 3 hydrogens, okay? And C, okay, so C has an integration number of 2, so not terminal, right, because otherwise it would be a CH3, and we see we only have 1 neighbor. So we're alpha to the carbonyl on the other side, but there's something going on, right? We only have 1 neighbor next door. That's a bit odd. Maybe our 1 neighbor could be A. And D. D, we have that very interesting, you know, singlet at, you know, very upfield. So no, you know, downfield shenanigans. And we have 6 hydrogens. So it looks like we have some type of CH3 action. However, right, it's not, so very, very, very commonly, right, you would see something like this. And this is like a T-butyl group. Because, right, you need a CH3, a CH3, and a CH3, and then right here by default, that's a quaternary carbon that has no hydrogen, so that takes care of the singlet splitting pattern. However, interestingly enough, we have only 6 hydrogens for our integration number for D, but we have no neighbors. So, one thing I think is very easy to, you know, maybe figure out is if we wanted to start with one end of our structure and we have our CH3s right here, this is peak D, how can we make it so that these 6 hydrogens have no neighbor? Well, let's put a double bond right there, okay? So that means that this carbon by default has no hydrogens, has no peak represented in our spectrum, and that then sets us to kind of go chug along because there's only 1 hydrogen here if I keep my chain going. So if I then think this is peak A, how can I then continue that? Well, I have to have 2 neighbors, okay? So a chemical shift handled by the fact that this is a vinyl hydrogen, okay? So then if these are my 2 hydrogens, I see I have an integration of 2 for my peak C, and does that check out? Yes, as long as I then have this to go along with it, right? And then if I just tack on 1 more carbon, this is my CH3 that could be found for the shift, or sorry, for the peak of B. So let me make sure I've stayed within my molecular formula. 1, 2, 3, 4, 5, 6, 7. 2 degrees of unsaturation, so the hydrogens will work themselves out. So not only did we get our degrees of unsaturation, but we got everything we needed. And I feel like most of these problem gang, I hope, you know, unless it's a ring with a ton of symmetry, if you can chew off one end and then find the other, the middle kind of works itself out, or you can at least get something on paper, be confident in your ends, and then figure the middle out, okay? So that was problem 2, on to 3. Hey gang, in problem 2, I realized I had a 14 there, it should have been a 12, so if you're wondering why that was there, that was just an accident, my bad. Okay, problem 3. So if we take a gander here, right, we see C10H14. So not a lot of hydrogens compared to how many carbons. So in doing our first step analysis of degrees of unsaturation, we can see, oh boy, we may have that magic 4, right? So when we see 4, we're thinking benzene ring. Tuck that in the back of our brains. Okay, so in taking a look right here, I hope you're locating what's going on in the 7 range. Your suspicions are correct. We have a benzene ring in this situation. So you guys see all this activity right there. And, you know, we see quite a bit of peaks. This problem of all the ones we've done together, the most peaks. So not as much symmetry going on. So I think it's safe to say we can slap a benzene ring right up here. And we can figure out what's going on. So in looking at ABC, just let's chew these off first. We can see we have one peak that corresponds with one hydrogen and then 2 peaks that correspond to more than one. So in benzene land, right, there's some symmetry with A and C, not with B. Okay? So that means that we have 2 positions represented here, 2 positions represented here, 1 position represented here. So that's a total of 5. So we have 6 carbons here, and it looks like then the other carbons are outside of this benzene ring. And it makes sense because we can see these are very downfield. We see 1 carbon that's fairly downfield, but then that kind of tails off. So this 2.6 also aligns with being benzylic. If you check out a chemical shift table, make sure you have it handy. Don't leave your house ever without it, right? So I know I'm jumping around a little bit, but if we take a look here, right, with A, we have an integration number of 2, but we only have 1 neighbor. We're a doublet, okay? So what I want to kind of do for now is just humor me. Let's have an R group right there. If we had an R group there, where could we identify A, B, and C as being located on this benzene ring? Well, the fact is B and C are triplets. That means they have to have 2 neighbors. A is the only one, which corresponds to 2 positions, that has 1 neighbor. So I'm going to go ahead and say A is right here and here, because that means we'd only have 1 neighbor right there with A, because the R group is going to occupy where another hydrogen would be. So A is in this position because it can only split with the hydrogen right down there, and there's symmetry. So 1 peak corresponds to 2 hydrogens, as seen by the integration number. So I hope you're seeing that there's symmetry here, and just based on that alone, I could assume that C is right there and B is here, because B only has an integration number of 1. And just to make sure that that checks out, right, this indeed is a triplet. These indeed are triplets. That works out. So what I'm going to go ahead and do is erase these because it's really kind of muddying our waters. So, and what I'm also going to do is I'm going to move this benzene ring out from here because it's kind of claustrophobic. So what I'm going to do is move this over here. We know we have a benzene ring. We know there's some R group right here. So we really need to figure out what D, E, F, and G correspond to. So luckily, I think we can identify what the tail end of this is. We have a methyl group, right? It's a triplet at 1. So as opposed to some other examples we've done where that's been a singlet or a doublet, here we truly have a CH3 that's going to have, what we can even do is kind of construct the R group over here. The one end will look like this. We have a CH3. There will be 2 neighbors, that CH3, to indeed make it a triplet. So we know this is G. Now what can we do to make sure F is this way? F is a sextet, which means it needs to have 5 neighbors. Well, there's 3 right there. And if we just lengthen our chain to be another CH2, this would take care of F as well. Because 2, 3, that's 5. That would make this a sextet. It's not very, it's in that realm of being upfield, slightly downfield. Wonder where that's coming from. But we can just keep on chugging. E, we're getting more upfield. Or sorry, more downfield, right? As we go from G, F, E, and D. So E is a quintet. So if we just, again, further the chain, we have 2 neighbors right here. This does satisfy what E is, because 2 neighbors plus, there's the 4 neighbors that E has. And last but not least, we get to D, and D's the carbon we thought might be the benzylic carbon. So if we were to hypothetically have this attached to a benzene ring, whoa. that would explain why it is more downfield and why we also see this downfield character kind of start to tail off as we get further away from the ring, or it increases as you go towards the ring. So, long story short, just by identifying that this was benzene ring solved most of this problem, but all we needed to do was 1, 2, 3, 4. That gives us 10 carbons total. This is our structure right here, and to finally label things more appropriately, this is A. We said this is B, this is C, and then it just goes D, E, F, and G. Okay, gang, that was problem 3. I think you'll see problem 4 is a bit of a cool down. It looks a bit weird, but I promise you it's kind of fun. Let's finish strong. And last but not least, problem 4 of part 2 of deducing structures from proton NMR spectra. Okay, so if we take a look here, what is going on? So let's get our degrees of unsaturation first. So we have C4H8O, plug into our handy dandy, not notebook, formula, and we get 1 degree of unsaturation. And we have 1 signal for everything going on here. Right, so integration number is 8, that makes sense because 1 signal, 8 hydrogens. So we see we're in ether territory with a 3.4 chemical shift. We're a triplet, integration number of 8, and it looks like we have 2 neighbors. Everyone's gonna have 2 neighbors, okay? So total symmetry looks like an ether, 2 neighbors, and 1 degree of unsaturation. So if you can think about this, the only way this would work with a double bond would be if we were like this. Because this would be 1 peak, but I hope you're thinking, 1, it doesn't even match our molecular formula. Also, the chemical shifts would be somewhere around 2-ish, right? So no go there. So this is an example where you have extreme symmetry and a ring can help. We also have, 2 of these. That's key to the problem. So sorry. 2 of those. My bad. So if we take a look here, how can we use 2 of these oxygens? We need to make a giant ether, a cyclic ether. So hopefully this idea came to mind. Okay? Because with this, we have 1 equivalent position. Okay? Good. 4 carbons total, 8 hydrogens. We have our 2 oxygens. We have, right, if we draw these hydrogens, you can see that every hydrogen has 2 neighbors. Triplet, 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 triplet. These positions all correspond to the signal A, and the ethers the ethers cause that downfield 3.4 chemical shift that we see. Okay, gang, and don't feel bad if you didn't get this, because I remember this was on a lab quiz I took in college, and it was one of those things I didn't get, and it was so frustrating when I saw the answer. I was like, I'm never gonna forget this problem. Haven't forgotten it yet. Gang, hopefully you got the explanations you were searching for. If you're watching this video, that means you've financially supported jOeCHEM. I thank you so much for using the website. I thank you even more for paying and supporting the website and myself financially. I am so happy you're using jOeCHEM. I hope it's helping you succeed in organic chemistry now. I hope you're using it and succeeding at organic chemistry until you're the very end of when you're taking organic chemistry 1 or 2. But if anything, I hope to see you all in the next video.